So as you can see here, I'm going to kick off the academic spotlight, particularly advances in STEM education pedagogy. So that's a big sentence, a big phrase. There's a lot one might do with this. And what I'm going to do, as you will see, is not say too much, but send it over to the people who actually do all this wonderful work and let them talk to you about some of the incredible things that they do with our students. And the emphasis on this is our students. But before I kick it off, I do want to say I think Harvey Mudd College is unique. That's a word I don't really like, but because it's getting misused all the time. But I'm not aware of any other STEM education that's provided in a liberal arts context. And that gives us a superpower. So what I want to convince you of is not only are we unique, but we are the best at delivering STEM education in this country, if not the world. And those are different things. Unique is not the best. Best is not unique. They're not always the same thing. In this case, they are. And I want to give you a small little sliver of why I think that's true. So I want to make a case. So I went to the Google and asked it to tell me if it said create a word cloud that will describe undergraduate education for liberal arts colleges. And this is what it provided. And as you guys all know, there's a lot of liberal arts colleges in this country. And what makes us special? Well, all these things definitely make us special. We do all of these things for sure. But I want to highlight two things that talk a little bit about the STEM part of what we do. They're small on this word cloud, but they're super important to us. So we do a lot of research, and I'm going to use clinic and research almost interchangeably in this context. We do a lot of this research, and I'm going to argue that we have global impacts. And if you don't buy that, if you think that's an overstatement, stay tuned for the next 3 talks. All right, so there's a lot of pedagogy that goes on. You've heard about some of the aspirations that we have. If you spend any time on this campus, you know that we are utterly student-focused. We're all about teaching our students and educating them. So we do that. One of the things that makes our education so special is the research, clinic opportunities, the hands-on experiences that we provide. Okay, so I want to highlight that a little bit. Well, I will not highlight it. My friends will highlight, my colleagues will highlight in the next few minutes. But I want to make that case. So I claim we're the best. Why would I say that? Well, lots of reasons. Let me give you a couple of examples. Here's a list of the PhD production per capita, so per student, PhD production in STEM PhDs. So that's a list from the National Science Foundation, and it lists them in order from top to bottom of who produces the most PhDs in STEM fields in the entire country. And in case you're missing the point, the top 3 are listed here. So we are firmly, if you look at the deltas on these numbers, we are firmly in second place here to 2 of our strong competitors who are R1 institutions. They are not focused on a liberal arts context in undergraduate education, and we are. Yet here we sit, right between Caltech and MIT. Unbelievable. Best. All right, that's an academic preparation that we provide for our students that allows them to be so successful in graduate programs, super important, but in fact, not all of our students go into graduate school. In fact, most of them do not. A lot of them go out into the world, and they get jobs, and they do really important things in those jobs. And so one very gross metric for how the world, the corporate world, the employment world views our students, this is a very gross metric. Okay? It doesn't capture everything, but if you go to payscale.com, the most recent data, we have the #1 pay of any school in the country. Our graduates, so in other words, our graduates have the highest pay coming out of an undergraduate institution from any school in the country, including all the R1s, MIT, Caltech, all these other schools. #1. Some might call that the best. Okay? And mid-career, we're at #4. Okay, so for the hundreds of schools in this country, we go from 1 to 4, from beginning to mid-career. So another metric which says we are doing extraordinary things at this institution. All right. We do this with a pretty even gender split, men and women, half and half. Okay? That's another thing where I think we distinguish ourselves from other STEM schools. And if you have STEM granting majors and half your students are women, guess what happens? So if you look at the graduation rates here, so graduates 2023, 2022, 2021. Okay, so I didn't want you to think I was cherry picking, so I've included 5 years of data here. And we'll just focus on this one, but what I've highlighted here is computer science. More than half of our majors are women. Engineering, more than half. Mathematics, more than half. Physics, more than half. I encourage you to do your own Google research on this and see how that compares to other institutions you might be aware of. It doesn't look like this. And to tell stories out of school, I did have another column here from another institution, which Harriet correctly convinced me we didn't want to embarrass our friends. So we don't have a comparison group. You can just Google it. All right. So I'm trying to make the case that we provide a world-class, the best education for STEM education in a liberal arts context. And one of the very, very, very important aspects of this is the research experiences that our students are deeply involved in. And so what you're going to hear in the next 3 talks are the work that Professor Hawkins does, the work that Professor Schultz does, and the work that Professor Duda, oh no, he's not a professor, he's a student. You'll think he's a professor by the end of his talk. He's a junior, and we're very excited to have Yvonne also giving a presentation here. So with that, I'd like to ask Professor Hawkins to come up. Excuse me, Professor Schultz, I'm going to get it backwards. Professor Schultz is going to talk to us about her work with students.
So I want you to imagine that you're in Africa and you're staring at this beautiful sunset. It's so idyllic. When suddenly you feel this really sharp pain in your arm. And what you're feeling is a tsetse fly that is using its mouth parts like a buzzsaw to drill into your skin and drink your blood. And if you're very unlucky, this tsetse fly will transmit deadly trypanosome parasites directly into your bloodstream. Eventually, those parasites will migrate to the region of the brain that controls circadian rhythm and make you very sleepy during the day, causing a fatal disease called sleeping sickness. Now, sleeping sickness is 100% fatal if it's untreated. And the drugs we have to treat it are not very good. They have really serious side effects, and they don't work against all strains. So if you wind up in a hospital with certain strains of parasites in your brain, they will treat you with arsenic, a derivative of arsenic. Now, I think the fact that we don't have good drugs for this disease is because it's a member of the group of neglected tropical diseases. These diseases affect 2 billion people a year, killing hundreds of thousands of them. They mostly affect people living in the global south. They mostly affect the rural poor. And historically, drug companies have not been motivated to develop drugs for people who can't pay for them. In the case of sleeping sickness, things are even worse because these trypanosomes kill cows. And folks living in sub-Saharan Africa, where this disease is endemic, are really dependent on these cows, both for subsistence and for farming. Billions of dollars are lost every year in gross domestic product from cows dying from this disease. So we really urgently need new therapies and new strategies to treat neglected diseases. And I'm going to tell you a little bit about our lab's efforts with sleeping sickness. Now, you might be saying, wait a second, I have an immune system. Why can't my immune system just get rid of this thing? And the reason is because the parasite is covered with a really dense protein coat. In my cartoon, that's red. And your immune system will make antibodies that will recognize that coat, and that acts as a tag for the immune system to say, this is bad, you should get rid of it. But the problem is that these parasites can change their coats. And when they do that, the immune system has to make a whole new set of antibodies against that new coat, and then the parasite can do that again and again and again, with the immune system always one step behind until eventually your immune system is exhausted and you die. Now, when the parasite moves into the fly has no antibodies. So the parasite gets a little bit lazy. It just expresses one invariant coat when it's in the fly. And that gave us an idea, which was, what if we could trick parasites in the bloodstream that are causing disease to act like they're in the fly? Then they would express this one invariant protein. The immune system would have a handle to get rid of them. And I know that sounds far-fetched, but we've actually been able to identify small molecule inhibitors that target proteins that regulate DNA, that turn bloodstream parasites into acting like they're in the fly, expressing one invariant protein. And when we put those parasites into mouse models of infection and they're no longer changing their coats, those mice live. So that's really exciting. But this initial molecule that we discovered is not going to work well in people. And so that got us wondering, what if there is an FDA-approved molecule that is safe, that is used to treat something else, that might do the same thing, that might make our bloodstream parasites act like they're in the fly? But to ask that question, we needed a really fast and efficient way to measure whether a parasite had an invariant coat. And so I pitched this project to my 2 undergraduates. They weren't yet in my lab, but I said, Maddie and Ellie, we can do some super fancy molecular biology so that every time a parasite expresses this invariant coat, it'll turn green. And we are so good at measuring whether parasites are green in the lab. We can definitely do this. And they said, this sounds really hard. And it also sounds like it's going to take a really long time. And it also sounds like it might not work. And I said, well, I mean, that's pretty accurate. But then they said, but if it did work, it sounds like it could really help people. And I said, yeah, you could be part of that effort. And they said, well, sign us up. And so they did this. They built this parasite, and they screened 1,500 FDA-approved molecules. And after a lot of effort, they were able to identify 2 of those compounds that turned our parasites green. And they also identified 150 additional compounds that had a really severe impact on parasite growth, stopped parasite growth. And we're so excited about this idea of repurposing existing drugs to treat not just sleeping sickness, but all neglected tropical diseases. And then with this in hand, we were able to go to the National Science Foundation to get funding to ask what genes are important for controlling this coat. And we turned this into a class. So at Harvey Mudd College, if you're in the advanced molecular biology class, you get to choose a gene that you think might be important for controlling the coat, and then you get to do experiments on that gene. And the student response to this has been really positive. They love doing experiments where they don't know the result. They love being the first ones to do it in the world. And they love doing experiments where they might actually help people. And now that we've discovered some of the genes that are important, we're starting to work with people who work in malaria, so with malaria parasites. And when we tweak these genes in mosquitoes, which are the vectors, the organisms that transmit malaria, we find that these mosquitoes cannot produce any parasites to transfer to a human host. And that is really impactful because malaria kills over 500,000 people every year, most of them children under 5. So if you were to ask me, can you promise me that your strategies are going to cure sleeping sickness or malaria? I would say, I hope so. But in science, we can't make those kinds of promises. But here's something I think I can guarantee, that every one of the students who have worked in my lab have worked on a really important problem that has the potential to have a really positive impact. And I have every confidence that they're going to go into the world, find the most complex, challenging problems, tackle those problems with the highest potential for impact, and maybe even solve them. And I cannot wait to see what they do. Thank you.
So you've just heard about the impactful work that our students are doing, led by faculty like Professor Schultz, in-house, newsworthy research. I'd also like to share with you some of the impactful work our students are doing on major collaborative work with partners at R1 institutions on projects that are globally important, such as air quality. So, despite decades of research, air quality is far from a solved problem. This satellite image, taken by a NOAA satellite last fall over northern India, captured an air pollution episode so severe it was seen from space. The fine particulate matter in this image is not 10, but more than 110 times the guidelines set by the World Health Organization. This is what that same region looked like in August, and this is what it looked like to be living through this nightmare. So pollution descends upon this region every winter through a consequence of agricultural burning, coal-fired power plants, traffic, and windless days. And this is not a problem limited to India alone. In fact, the World Health Organization estimates that 99% of us are breathing air that exceeds their guidelines for fine particles and hazardous gases such as ozone and nitrogen oxides. And because of air pollution's toll on our bodies, estimates place it as second only to high blood pressure in terms of risk factors for death. And in fact, really recent work on the exposure response function between air pollution and health estimates that we have a more serious response than previously thought. So it's probably worse for us. And although the majority of the 7 million annual deaths from air pollution belong to adults over age 70, there were over 700,000 deaths among children under the age of 5 due to air pollution in 2021 alone. So it's no surprise that air pollution research attracts major headlines and major funding. Even before January, when many in LA were asking, what am I breathing? What's in the air? We were paying collective attention in the US and abroad. Now, air pollution research takes a village. The complex mixture of gases and particles, which vary in all 3 dimensions in space and in time, requires pretty much every tool you can imagine to differentiate what's in the air right now from what can we expect in the future. One valuable but costly tool is the field campaign. So experts and their teams of students will spend months preparing to deploy instruments in protective shelters, on tall towers, in ships, and in aircraft, all after years of planning to select a site and obtain the necessary funding. And the campaign, the field campaign, is ephemeral, most lasting only 6 to 8 weeks. But much of what we know about the processes that govern air pollution have come from these short, intensive bursts of activities. They're also exhausting. During a field campaign, your only priority is to get the highest quality observations for that short period of time. And I should know, I've been participating in field work like this since I was a graduate student, and now as a faculty member here at MED, I get to involve students in this type of work. In summer of 2022, Drew, Sydney, and I spent about 5 weeks bouncing back and forth between Paris and its forested outskirts as part of the Across campaign, targeting the understanding and intersection of Paris's urban pollution plume with its surrounding suburban forests, which create a complex, rich mixture of organics and interesting atmospheric chemistry. And we certainly learned a lot. But what about events that are unpredictable? What if the weather doesn't cooperate? And how can you compare the results from one campaign to the next when the instruments and even the players can change? What if we were able to obtain some of the essential measurements of air pollution, typically only associated with a field campaign, all of the time? You could compare summer, fall, and winter, or 5 years of summers in the same location, or already be sampling when a wildfire brings smoke into the area. And what if you did that in more than one location so that you had directly comparable results with the same methods and the same techniques? Well, you would need a big team and a lot of funding. So Harvey Med teamed up with 12 other institutions, all R1, to make this dream a reality. We have added 4 instruments, all measuring previously uncharacterized air pollution metrics, to each of these 12 sites across the US, which operate on timescales of minutes to hours instead of days. And this research is catapulting progress in things like satellite ground truthing, chemical transport modeling, and the fundamental processes that govern this air pollution. My team has been responsible for one of a trio of sites located in Southern California at Joshua Tree National Park. Prevailing winds from the area we are in here now will bring pollution eastward over to Joshua Tree, causing regular exceedances in the air quality in this very protected Class 1 airspace. The students involved are the only undergraduates involved in this work, and my student lead, Eleanor Bentley, was doing all of the same things that graduate students were doing at the other 12 sites to set up our observatory, from installation of the instruments, calibration, and data analysis. Eleanor even served on the SOP team, ensuring that we had standardized procedures across the network for the highest quality, consistent observations for the whole team. And it's a good thing we did. In January, we saw 2 communities in LA go up in smoke in a matter of hours, vaporizing the entire contents of people's homes and filling the air with an absolutely toxic soup of hazardous chemicals. Everybody was checking maps like this one for the air quality index for that day. But the air quality index doesn't tell you what's in the air. Our instruments do. On a timeline unthinkable for deploying a field campaign, our network was reporting lead and chlorine and other hazardous compounds in the air, earning us the attention of the New York Times, which shared one of our data sets like this one, showing elevated lead briefly, but, exceeding EPA guidelines, and also telling us when things had died down. Because of the press attention and the demand for the data, within 24 hours of the New York Times article, our team was ready and available to make this preliminary data live, public, fully accessible to folks living in these areas so they can see when things like lead, bromine, and chlorine had returned to safe levels. So, like the Nye, I can't promise you that better measurements, more chemical detail will lead to better models. And I will definitely not promise you that better data will lead to better policy. But I can promise you that in the 14 years that I've been working here with students on this project, each of them has had a chance to be part of something bigger than us, working on a problem that affects billions of people and learning that science can do good in the world. Thank you.
Yes, I will talk about, I'm Ivan, and I will talk about Sokil, our startup that utilizes innovative drone technologies to accelerate landmine detection in Ukraine and around the world. As you can see, I'm Ukrainian, and this is Ukrainian clothes, and this is the map of Ukraine. And it's a map of Ukraine and landmine contamination in Ukraine. And I'm from right down here, the area marked in red. Growing up in that region, I loved it. We have national parks, we have access to 2 different seas, we have sand dunes, we have forests, we have prairies, and it was a huge part of who I am and who I grew up to be. However, as you can see on this map, it's all red. So even once the war is over, once we reclaim our territory, my kids in the future, when I come back to live there, would not be able to enjoy the same nature as I did. And it's because Ukraine is contaminated with landmines. I would not be able to let my kids play in a forest. And another problem is that the landmine clearance is really slow. Working with a metal detector, scanning for every signal of a metal detector is still the status quo. And then imagine somebody using a metal detector to scan every square meter of an area of a state of Illinois. Think how long that would take. And it's also a really laborious, dangerous, and expensive process. But there is hope. The government of Ukraine estimates that only around 10% of the area that is suspected to be contaminated with landmines is actually contaminated. So theoretically, if we find a method to survey all that area and be able to differentiate where there are mines for sure and where there aren't, we would be able to release 90% of that land to use agricultural, humanitarian, and we would be able to prevent thousands of lives being lost and billions of dollars of economic impact annually to Ukraine and in the future around the world. So we thought, big idea, what if we use drones? Drones are autonomous. They allow us to move fastly through the field, scanning fields really fast. They're also safe. You don't have to have someone on the ground doing that scanning. And they also use science to make conclusions and not somebody hearing a signal from a metal detector. So all around a great idea. But it's complex, and it requires engineers like at Harvey Mudd to actually do the work. And we thought, okay, we can imagine that we make a map like this one and we find areas that are green and those areas can be released, and then we find areas that aren't, and this is the information we provide to supper groups, to demining groups on the ground, and they can use this information to understand, do I need people on the ground here to clear or not? And we involved engineers at Harvey Mudd. Xander is my co-founder, and we started from getting a Shanahan grant that gave us some resources to start early prototyping. And early prototyping in college is our dorm room. Just having a little drone, a little a little bit of equipment and involving professors, faculty. Prof. Galicia, sitting right there, was with us from the very start. Here's the first day that we met, and he gave us access to his laboratory. So we could really start early on having a lot of equipment and resources that accelerated the work and prototyping that we could have done prior to the summer, where we took advantage of the summer entrepreneurship studio led by Prof. Dodds right here, which allowed us to get out in the field. This is us in Oklahoma with leading demining organizations in the US developing drone technology like us, and our system sitting right here. And we were able to do testing and validate the performance of our system, and also do some more prototyping and research and development to actually make something that can go to Ukraine for testing, because it's a very difficult process. And here's Prof. Dodds and Zander looking at our PCB for one of our prototypes. And then we thought, okay, our initial technology can only tackle metallic mines, but not all mines in Ukraine are metallic. And we turned to Harvey Mudd Clinic program, and we have 6 bright engineers right there on the picture developing a laser-based system that can detect not only metallic but also plastic mines under heavy vegetation. And it's an unsolved problem. Nobody in the world has been able to find a solution to do that, and we might be the first ones. And as we're looking into the future, we're doing testing in Seattle, Washington. This is one of the pictures, and this is the results that we got. And we get pretty good detections, and we validated and wrote up a report on our system and got to the point where now we are ready to actually send it to Ukraine for initial testing. Some more ITAR work, and hopefully we can get to do some testing there already this May, June. And the most important thing to say really is this wouldn't have been possible without Harvey Mudd students, Harvey Mudd faculty that have been there along with us during this wild ride and provided all the resources to us, and importantly, Harvey Mudd College that provided financing, access to resources, both financial and technical, and access to the bright faculty to whom we can turn when we have questions and try to do this important work. So really, I want to say thank you to Harvey Mudd College for helping me to bring this to life, and also to all these people that make Harvey Mudd College to bring such projects to life, and I hope there will be more. Thank you.